which is chapter 5, angle modulation. In angle modulation, we will learn about frequency modulation and phase modulation. Okay, let's have a refresh back on what is amplitude modulation, our previous chapter, and our current chapter, which is frequency modulation. Okay, originally the AM was designed in 1870s, which is a long time ago, but FM is in the 1930s. Okay, so the first amplitude modulation was designed to transmit an audio transmission. Alright, so in the differences, we know that in AM, so a carrier is modulated in amplitude. Okay, but in FM, the frequency is modulated. The frequency of the carrier is modulated. Okay, so both can be used to transfer analog and digital communication, and also the frequency range for AM is quite low, up to 500 until 1700 kilohertz, but FM is around 88 to 108 megahertz, as you can see in our car radio, right? Right. The next one, if we want to compare about the bandwidth, the largest of AM occupied, the bandwidth would be twice of the bandwidth of the message signal or modulating signal. But in FM, it's only not twice, but it has to add the frequency deviation. The frequency deviation is 75. The frequency is 15, so 75 plus 15 multiplied by 2 is 180. Alright, so for AM, it just double, right? The complexity, of course, in AM, it's simpler, but FM would be more complex because we have to vary the frequency and also the phase. We have also instantaneous phase and instantaneous frequency. Alright, so as we know that in AM, it's very susceptible to noise, but FM is less susceptible because this design was created to improve the AM modulation. Right. So now we are going to focus on the main agenda, which is angle modulated. So when we are talking about angle modulated, means that we're focusing on this side. Yeah. Wait a minute. Alright. So this is the angle. Part. Okay. So the information will be embedded in the either phase or frequency. Okay. So what's that mean? Every modulating signal differences, we are going to have instantaneous phase and instantaneous frequency. Okay, in the instantaneous phase, okay, we know that this is the phase part and this is the frequency part, but two of it we call it as angle modulated. Okay, so this excess phase will refer to the modulating signal or representing the modulating signal. Okay, and of course we are going to have different frequency at each component or each modulating signals. That mean we are dealing with instantaneous frequency. So in this instantaneous frequency, it will be depend on the rate of change of the phase. Okay, so this two is this phase, which is we have phi I equivalent to 2 pi fi t. So I is referring to the instantaneous phase, means it will change. Okay, so the instantaneous frequency will depend on the rate of change of the phase. Okay. So again, the amplitude is constant. Alright, so in this case, the modulated waveform will not resemble the message, but the frequency and the phase will bring the information of the message signal. Okay. Okay, so just to do some refresh. So this is the phase, and this is how we calculate one period. Okay, so one period equivalent into 1 over f. Okay, f equal to 1 over t. Alright, so the relationship of phase and frequency is actually, if you multiply frequency and time, we will get the phase. Okay, so again, this one related with f and time. Okay, how to measure the period. Okay, so actually phase and frequency is interchangeable, right? So now we go into each of the modulation type, which is the first one is phase modulation. Okay, in phase modulation, remember I showed just now the excess phase. So the excess phase of this carrier varied with the message signal. Okay, so let me show you again. So this is the excess phase. Okay, so we will vary that part. So that's mean the phase theta t will equivalent to kpst. So this kpst is new to you. Only in angle modulated we have this phase sensitivity and frequency sensitivity. Okay, so what does that mean? We vary the signal, but we have some coefficient or factor that contribute to the how much phase changes will affect in this excess phase. Okay, so since we want to deal with this normalized signal, so this is normalized signal Sn. Okay, Sn. So we want to name it as Kp max St multiplied by Sn, or we simplify as delta phi max multiplied by Snt. Okay. Okay, what is maximum St? Alright, so we always see this maximum St, minimum St, right? So in this example, okay, for example, we have a mixture of signal. Okay, maximum St is the maximum value of the signal. So let's say this is St signal. Okay, and the minimum St will be the values at the minimum. Okay, so we want to normalize the signal so it will be standardized. Okay, so it will be better for us to analyze in the concept of normalized signal. Okay, so remember the terms of delta phi max, which is the maximum phase deviation or maximum phase shift. Okay, and also the normalized signal. Okay, so the conclusion for this phase modulation, so if we want to do a phase modulation, we will have the carrier AC cos 2 pi FCT plus, okay, this plus will make a difference to our signal. So this means it will refer to what is our information that we want to read or we want to send. Okay, so as far as we concern, we have to know what is the maximum phase deviation or what is the phase shift and what is the normalized signal. What is maximum phase deviation is actually like how much phase you want to allocate for these changes. For example, the message signal maximum value is 10, and then I want to allocate 10 phase difference for this 10 volt. Okay, and the lowest of that value I want to give, of course, is for 0. Okay, so in the middle we will quantify what is our message signal. That means, for example, I have a 1 meter cloth and I want to divide into 10 students. So I have to know what is the capability of that cloth. Okay, how big is that cloth? Okay, to be capable to representing the students' number. Okay, for example. Okay. So first modulation, this process with changing of the phase of carrier. The carrier of the phase we will change, so the information is inside the phase. Alright, so the amplitude of the carrier is constant. Alright, the modulating signal only changes the phase of the carrier again. Okay, so the phase manifests itself as a frequency change, but the instantaneous frequency change is proportional to the derivative of the amplitude. Okay, so I'll show you what that means after this. Okay, the bandwidth is higher than 5M. Alright, so this bandwidth part we will go in the next class. Okay, so just now we have looked into the equation how we want to do the phase modulation. Okay, so for the phase modulation, you have to remember that there will be a instantaneous phase and instantaneous frequency. So how to find that instantaneous phase? It will be 2 pi fct plus 5 which is this part. Okay, so you just take directly for this part. So instantaneous phase at phase modulation, so you want to know what is this phase. But what is frequency, instantaneous frequency? Okay, because inside here there is a frequency. Okay, okay, so what we want to do, we have to find this instant frequency is the FC, of course, has to be there, and then the delta phi max divided by 2 pi multiplied by the derivative of the normalized signal. So means we derive this part, okay, ddt, to find the instantaneous frequency. Right, so this is an example of the modulating signal. So this is the carrier. So now we want to change the phase to be resemble the modulating signal. Okay, for the alright, next one just now is phase modulation. Now the second one is the frequency modulation. Alright, in the frequency modulation, there will be instantaneous frequency and of course instantaneous phase. Okay, so this instantaneous frequency will vary with the message signal. Okay, remember, not amplitude anymore, in the frequency. Okay, so instantaneous frequency will be FC, of course, the carrier, plus KF max ST multiplied by the normalized signal. Again, just like PM, FM will be whatever the maximum ST multiplied by the frequency sensitivity and also SNT. So these two parts exist also in the phase modulation. Okay, so now we want to know what is the instantaneous phase of the frequency modulation. Alright, so phi IT, the instantaneous phase, will become 2 pi fct. Just now we derive, right? Right now we integrate plus 2 pi delta fx. We integrate this part, integration of the signal itself. Okay, so now we have instantaneous frequency for FM, instantaneous phase of FM, and also the FM modulated signal itself. Okay, right now if you can see here for instantaneous phase, it will be inside the FM modulated signal. Okay. Alright, so of course we will change the frequency. Okay, this one silap phase potong. Alright, the frequency of the carrier, and then the amplitude will be the same. The modulating signal changes the frequency of the carrier. Alright, so bandwidth, and we have to know the frequency deviation. Okay, so in conclusion of FM, how to find the modulated signal of FM, it's using this equation. What is the instantaneous phase? You have to use the phase here, and then instantaneous frequency is the FC plus delta Mx SNT. Okay. Alright, so this is how it looks like. Okay, so for FM, it's easy for me to explain because if you see here, the maximum modulating signal will be equivalent to the highest frequency. Okay, while the lowest values of the modulating signal will be equivalent to the lowest frequency. This means slow oscillation, right? So this one is faster oscillation. So in between that, we can, for example, this is 10 again. So this is minus 10. So we can divide this point into certain values of frequency. So that the 10 that I gave you for the maximum frequency, that is the maximum frequency deviation. Okay. Whilst how many slotted here, how many points that I want to give to this 10 is defined as frequency sensitivity. Okay, like very sensitive, or just we have to plot 1 or 2 point, or we want to be very detailed, like 50 point, for example, right? Okay, so this FM band allocation is easily can be applied in our frequency radio. So for example, this starting from 88 megahertz, we're gonna have the first radio station, and then there is a band gap here, a few frequency that is null, so we want to have a gap between station, and then here 91.5 is Ikim, or we have Zayan here at 104.9. Okay. Alright, so actually these FM and PM are interchangeable, or we can have a signal. Okay, if we have this phase modulator, when incoming here, we have integrate the SN and multiply by carrier. So not this is not multiplication because this is not mixer, but a phase modulator. So we'll get an FM signal. But if we have a frequency modulator and we derive the signal here, we can have a PM signal. Okay. So how do we see that? Because there is a component of rate of change of the phase is equivalent to frequency. So when we want to have phase, we will integrate the frequency. Okay. Okay. So this is the key points in FM and PM. This table I got from the textbook. Okay. So the key parameters, we have to know what is the phase sensitivity, frequency sensitivity, and also what is the max frequency deviation and max phase deviation. Alright. And then what we have to know, what is the excess phase. This is the extra part, like 2 pi FCT plus what, okay, and then this win 2 pi FCT plus what, so the excess phase, right? And then in PM, we also have the instantaneous phase and instantaneous frequency. Same also with FM. We have instantaneous phase and instantaneous frequency. Alright, under the modulated signal, we can have it by knowing the delta phi max SNT and also 2 pi delta F max and integration of the SNT. Okay, S, remember what is S? Is the modulating signal. Alright, for example, we have this simple message with the values of -1 and 1. Okay, this is message signal. If you want to do the FM modulation, okay, FM modulation, that means we just have to represent the highest value with high frequency and lower value with low frequency. Alright, for PM, since we only have two values, okay, so we can have a 0 phase shift and minus 90 degree. So easy for you to see if it's only two. But remember, if it's like 10 values or 10 different level of modulating signal, we have to divide this phase shift. If you want to define the maximum is 180 degree. So now you have to divide it by 10. So every changes, we change 18 degree, right? So that is how we understand the FM and PM signal. Alright, so let's say we have a signal, a sinusoidal signal, simple one, cos 2 pi fmt with the amplitude modulation of AM. Alright, so the formula for FM, if you see here, FM, yeah. So AC cos 2 pi FCT, 2 pi delta F max into signal. So delta F max here is defined as, because this is cos, when you integrate cos, it will become sine 2 pi fmt divided by its coefficient, which is fm. So here beta here will represent the delta f max divided by the fm is from the integration of cos. Okay, so now this beta or modulation index we will see later in our next class. Okay, so if you want to do a PM signal, modulated signal, the formula is here. AC cos 2 pi FCT plus delta max SNT. Okay, so the 2 pi FCT delta max cos, just straightforward, take the value here, signal. Okay. Okay, if SNT, for example, in this case, is not given the maximum SNT, you just take the signal. Okay. So now we have modulation index for FM beta delta F max divided by FM. Okay. For PM, the beta is delta max, which is the maximum phase deviation. Okay. Okay. But remember, okay, this equation is only for cos. If the signal is a cos 2 pi fmt, else you have to integrate this one as the signal and this one as the SNT. Okay. Alright. For this sinusoidal modulation, just now for AM cos 2 pi fmt, the instantaneous frequency, if you see in this slide, also I have put this equation or clearly in here. Okay, so this 1, 2, 3, okay, you have to memorize instantaneous phase. Just follow the equation 2 pi delta F max, okay, and then this is you got from the SS or SN, and then you have to derive the SNT for PM. Okay, and then for instantaneous phase, you have to integrate the phase and the cos you can take directly. Okay, so easy for you. But I think this time the result, the exam can see the formula. So better if you can just understand, okay, and you no need to memorize, right? But at least you understand where to get these values, right? So again, if you want to calculate the power in angle modulated, how we get this equation, AC squared divided by 2 is by, for power, usually what we do is we have to, this is for the signal values of cos, yeah? Cos squared, we squared the signal and integrate, multiply by 1 over 1 period. Okay, so it's already simplified for you. So if you want to calculate, the power is equivalent to AC squared divided by 2, right? Okay, for FM and PM, obviously the comparison is we have this maximum frequency deviation and maximum phase deviation, and then here the frequency of the carrier is modulated, and here is the phase of the carrier is modulated. So in modulation index will increase if we use FM as we change this modulation frequency, but modulation will remain the same since we are dealing with the phase modulation. Okay, so this example I've shown the square wave. square wave. So we want to know what is the values in numbers. Okay, so the delta phi max is 5 hertz. Okay, so that's mean we want to change from delta f max is maximum frequency deviation. Okay, so means the maximum frequency we will give is 5 hertz. Okay, and this one is pi over 2, the maximum phase deviations. Okay, so the maximum pi over 2 will represent the maximum number of the modulating signal. Okay, so since the Sn is only 1 and minus 1, the square wave value is 1 and minus 1. So FMT, you substitute here, the FC is 10. Okay, and then this is minus 1, you integrate, delta F max is 5. Okay, and then for PM, 2 cos FCT, FC is 10, delta phi max here is pi over 2. So you change, each one will be plus pi over 2 and minus pi over 2. Okay, and for this one, 30 pi t and 10 pi t. Means the highest will represent 30 pi t and minus 1 will be 10 pi t. And this one, for 1, we use pi over 2, and the minus 1 we're using minus pi over 2. Alright, for example number 2, it is a modulating signal. The modulating signal or message is cos 2 pi t. I think we also have this, go through this example. And the carrier is 10 hertz, alright? So 10 hertz with the function of cos. Right, the phase and frequency sensitivity is 5 hertz and also 2 pi radian per second. Okay, right now be careful because the ST is in the terms of cos 2 pi t, right? The first one you have to derive is instantaneous frequency for PM and FM signal. Okay. Okay, the first one, write expression for FM and PM signal. The second one is the instantaneous frequency. Okay, so write expression, you just jot down the equation, but be careful, this side is due to the derivation of the cos. Okay, this one you SNT. Okay, this is the integration of cos. This is the signal itself. Okay. Okay, when you substitute, delta F max beta is here 5, and delta phi max is 2 pi. Okay, this is integration, and then this is the this is 2 pi FCT. Okay, FC is 10. Alright, next one you have to derive the instantaneous frequency. Okay, each of FM and PM have its instantaneous frequency. Okay, but for FM you can directly use the signal cos. For PM you have to derive the signal here. Okay, so now the cos will become sine. Okay, alright, so now it's already modulated for you. It can be FM, it can be PM. So the function is here, 2 cos 2 pi, this is the FC, okay, and this is the FM, okay, plus something, yeah. So determine beta, delta F max and delta phi max. So we just compare this equation with the original equation. So from this one, so we want to find beta first. Beta is here, okay, so this is the value of beta. Beta is equivalent to 5. And then we want to know what is FM. So this is FM, but this is 2 pi FT. Okay, you have to divide it by 2 pi. Alright, so delta F max is equivalent to beta multiplied by FM. Or you also know beta equivalent to delta F max divided by FM. Okay. Alright, so we can know delta F max by beta multiplied by Fm. We have beta, we have Fm. Alright, maximum deviation is we compare this one and this one. Alright, so we got 5. Right. Okay, so I'll just stop here. It's already 30 minutes. We will continue for the spectrum of angle modulated in next class. Okay, if you have questions, you can always ask me personally. Alright, Assalamualaikum warahmatullahi ta'ala wabarakatuh.